Here is the displacement. Sorry, I'm doing the revision sheet I gave you the other day. Now, first thing to note is that this isn't distance, it's actually displacement. Okay, they actually made a mistake in the question, and I'll explain why. Distance, for example, when I go to school, so let's say this is home and this is school, and school is, let's say, 800 meters away. Okay, so what should happen here is when I go to school, my distance goes up because I'm traveling to school. So my distance goes up 80 meters. And then when I return home, it means I travel another 80 meters, which would be 160 meters total, which means that the graph will have to go up to 160. Okay, so just to rehash that one more time. When I go to school, what should happen is my graph will go up because this is a distance time, if this was a distance time graph, when I go to school, the graph goes up 80. Okay, and then when I return home, the graph will go up another 80. Distance graphs can only ever go up. However, displacement is different. Displacement is how close you are to home. So in cases like this, displacement can go up and down. Okay, so we'll get onto this question now. All right, so this is a displacement question, not a distance question. Because you can't undo the distance you run. Okay. Name an instrument that could be used to measure the time taken for the journey. Okay, obviously a stopwatch. Okay. Calculate the average speed from point A to point B. Well, here's point A and here's point B. Look across and we can see that he goes from 0 to 100. So he travels 100 meters. That's using the y-axis. And then use the x-axis. So see the way B, directly underneath B is the 40. So B is the point 40, 100. This means you traveled 100 meters in 40 seconds. Okay, so it's 100 meters in 40 seconds. Okay, so you do 100 divided by 40, which is 2.5 meters per second. Okay, and resume. So, describe the cyclist motions between B and C on the journey. Well, B and C, he's at 40 seconds, he's 100 meters. He's traveled 100 meters, and after 60 seconds, he's still 100 meters. Basically means he was stationary for 20 seconds. He didn't move for 20 seconds. Stationary for 20 seconds, or he didn't move for 20 seconds, whichever one you want to say. The cyclist's speed as he travels from point A to point B was less than the speed from point C to D. What evidence in the graph supports this? Well, it's known as the slope in a distance or displacement time graph. The what's called the slope is how fast you're moving. So see A to B here, and see C to D here. If I was to move A to B towards C to D, you can see that the slope isn't as steep as C to D. So all you need to say there, C to D has a steeper slope. Has a steeper slope. Than AB. Now, next question is, what do the cyclists do at point D? Well, at point D, you can see that you're going in the reverse direction now. You're starting to go down. I think this means that the cyclist returned from where he started from, because it comes back down to a 0. See, it's 120, 0. After 120 seconds, you have no distance away from home, so you're back pretty much where you started. So you can say cyclist returned to where he started the journey. Or cyclist started to return. I suppose at point D he hasn't returned yet, so cyclist started to return home. it's like the start of return back to where he started the journey. Okay. Because you can see that D is the only place the graph goes downwards, okay? So that means he's returning home. When you're on your way up in a displacement, when you're on a way up in a displacement graph, you're going away from where you started from, and when you go downwards, you're returning back to where you started from. All right, we're looking for acceleration. There's a formula for acceleration. It's final velocity minus initial velocity over time taken. So your final velocity is 36. Your initial velocity is 12. You need to know this formula off by heart. The time taken was 3 seconds. So therefore, it's going to be 36, take away 12 is 24. 24 divided by 3 is 8. Please remember the units for acceleration. You need to learn this off by heart. It's meters per second squared. Okay. Now, I obviously have a graph for this one. So need to make everything a bit smaller. Here we go. Next question. Need to make this a bit bigger now. There we go. Now, let's see how we're getting on here. Okay, we have two athletes. The table shows two athletes, Orla and Molly, during a 100-meter race. The distance and time are recorded as shown. Now, they both start off as 0-0 because it's a 100-meter race, I suppose. So you could start this off at 0-0 if you want, but there's no indication in the graph you start off at 0-0. So they both have the point 420. So both Orla and Molly have the time 420. This means after 4 seconds, they're 20 meters away. They both have the time 840. 8 meters away, they're 40 meters. Sorry, 8 seconds in, they're 40 meters away. Then things change because after 12 seconds, Orla is 60 meters away, but after 11.2, Molly is 60 meters away. And then finally for the for 80 meters, then 16 seconds in, Orla is 80 meters away, and 14.4 seconds in, Molly is 80 meters away. And finally, after 100, to get 100 meters away, it takes Orla 20 seconds, while it takes Molly 17.6 seconds. Okay. So there's two sets of data here, okay? So I'm going to highlight the points for Molly. So these are Molly's points highlighted in yellow. And then these are Orla's points highlighted in blue. Okay, I'm going to have to graph this. I'm going to start off with the blue points. And hopefully I'll probably drag them. Oh no. All right, let's do this. So where it's 420. 420 is here. Okay. 840. 840 is here. And then we have 1260. 1260 is here. I think the next one is 1680, which is here. And then finally 2100. So this line I'm about to draw, this is I believe this is going to be Orla's time. So this is Orla's graph I'm drawing right now. Now the points given, you could draw it like this, no bother. Now you could be excused for going back to 0-0 because you know they both started off, it's a 100-meter race, so they both started off at 0 seconds and 0 meters. So you would be excused for doing that if you want. But I'm just going to stick to the points they gave me in the graph here, okay? Next thing we're going to do is Molly's time. Molly's graph. And I'm going to use red lines for this one. So they have the same first 2 points. So Molly is the same as Orla for the first 2. And then it varies after that. So it's 11.2 seconds. Now, how am I going to do 11.2 seconds? Well, halfway between 11 at 10 and 12 is 11. and then a small bit above 11. So I'm just going to roughly do 11. 11.2 is pretty difficult to pull off. So 11.2 and 60. So it wants me at the 60 mark, just around here, as best you can. Because 11.5 is halfway between 11 and 12. So just go halfway of halfway. Right, so around here. Okay. Then the next one point you want after that is to want me to go 14.4 for 80. So 14.4 would be roughly halfway between 14 and 15. 14.4 and 80. So around here-ish, I'd say. See the way if you drop down the line, see the way I'm roughly, sorry about that, guys. See the way I was to drop a line here, I'm roughly at in between 14 and 15. So that's what I'm looking at. I'm trying to stay in between 14 and 15 there, okay? Just under halfway between 14 and 15. So you can see these extra points appearing now. And finally 17.6 and 100. Well, 17 would be here. So 17.6 would be just over halfway between 17 and 18. So if you're using if you're trying to help yourself here, you could draw a line up like that, and 17.6 and 100 would be around here. This point here. Okay, and then you're done. So next we're going to do the red line, and this is for Molly. So you can see that both lines have the same starting off point, so to speak. And then all of a sudden the red line goes this way and it maintains its distance. So you can see the red line breaks off from the black line. Okay, the red line becomes steeper. This means that the red line is moving faster. It's clear to see that Molly is moving faster than Orla, because Molly does it in a quicker time compared to Orla's. Molly does it in 17.6 seconds, while Orla does it in 20 seconds. Okay. So calculate Orla's average speed. Well, it's distance over time, so it's 100 divided by 20. She does 100 meters. So speed equals distance over time. So it's 100 divided by 20, which is 5 meters per second. Which athlete, Orla or Molly, has constant speed throughout the race? It's Orla who has the constant speed throughout the race, because her slope of her line never changes. Orla. The slope of her line never changes. Or you could say, it's clear to see that Orla goes up in 20s all the time. See? Oh, sorry, every 4 seconds for Orla results in 20 meters. So you could also say that every 20-meter jump is a jump for 4 seconds in Orla's time. So you can say every 4 seconds she travels 20 meters throughout the race. Okay. There's anything else on this one? Whoop. All right, so we have another graph here. Sometimes they love the graphs. So let's do this. Okay, in a soapbox competition, a driver races against the clock straight down a track. Okay, so soapbox is a competitor, a driver against the clock straight down a track in the vehicle with no power source. So soapbox derby is down a hill. The table below gives the distances from start travelled by the driver at various times down the rundown down the track. All right, so we have points we need to graph here. Okay, so the points are 0, 0, 4, 6, You're doing time on the x-axis and distance on the y-axis. Then you have 8:14. You have 12:24, 16:44. He should go faster as the race goes on, because by the time you reach the bottom of the hill, you should be at your fastest point. Okay, so we'll see what happens in this graph. Okay, so let's graph this 0, 0, 4, 6. So remember, see the way there's 5 blocks on the y-axis? In between 10 and 20, there's 5 blocks. So 5 blocks is worth 10. This means 1 block is worth 2. So if I was counting up the y-axis, it would be 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. You got to go up in twos, okay? So to get 6, all I need to do is go up 3 blocks, 3 of the small blocks. And keep your points as small as possible. It prevents errors, okay? 4, 6, 8, 14. 14 will be there. 12, sorry, what to do? 4, 6, now I'm on 8, 14. Oh wait guys, I made a mistake there to start actually. It's 4, 6, not 2, 6. 4, 6 is there. 8, 14. Remember, so it's 12, 14. 12, 24. So 24 would be 22, 24, 2 small boxes above the 20 line. 16, 44. So 2 small boxes above the 40 mark, and then finally 20 and 100 right there at the top. So guys, this is a curve, not a straight line, so you gotta go through the points as best you can. It's really hard for me with this drawing kit, but I'll give it a go best I can. Okay, and make sure you do not use a ruler for this. Okay, it's important not to use a ruler. And there you go. So there's our graph there. Okay, next question. Find the time taken for the vehicle to travel 80 meters per second. 80 meters. I think it wants us to use the graph as well. Find the time taken for the vehicle to travel 80. Alright, so what you can do is you go to 80 meters, like so. Now you're allowed a margin of error here, because sometimes the graphs aren't drawn as strongly as they could. And then we go straight down. Now, roughly 19 seconds, halfway between 18 and 19. Okay, so you say roughly 19 seconds. Calculate the average speed for the vehicle during the last 4 seconds of the run. Average speed for the last 4 seconds of the run. So get this, in between, you're talking about 16 to 20 seconds. We have these 2 points here. So it travels 100, take away 44. It travels 56 meters in this time. So speed equals distance over time, which would mean it travels 56 meters in 4 seconds. 56 divided by 4 is 14, I believe. So 56 divided by 4 divided by 4, 14 meters per second. What's the difference between speed and velocity? Well, velocity is speed in a given direction. So for example, if I said a car was going 15 meters per second, that's speed. If I said the car is going 15 meters per second in a direction northwest, that's velocity. So velocity includes a direction. If I get rid of the direction, then it's speed. Okay, great. Now let's move on to the next one. Now, what do we have here? We got another one of these type of graphs, the tram graphs, or the speed time ones. Okay, now I'll bring that downwards. Make this a bit smaller. So I can see the graph going downwards. It's a speed time diagram. So this is different than the ones we've done recently. Okay, so this is a speed. So this one is a speed. This is not a distance time graph, this is a speed time graph. So things are different this time, okay? So let me explain what this means. The point 0, 0 means that your speed is 0 when time is 0. Time is 0, speed is 0. This here means after 40 seconds, your speed is 10 meters per second. And this here means after 100 seconds, your speed is still 10 meters per second. But you got to remember, you spent 60 seconds, which is 100 minus 40, you spent 60 seconds traveling at 10 meters per second. You're not stationary. It just means your speed isn't increasing. So you would have traveled 600 meters in the region M to N. So just be careful that in a distance diagram, a flat line means you're not moving, but in a speed diagram, a flat line means your speed just isn't increasing, but you're still definitely moving. Now this one's O to P is 140, 15, and P here is 160, 15, and then finally Q is after 200 seconds, our speed was reduced back down to 0, which means we stopped. Doesn't mean we went home, just means our speed is 0. Okay. Now, what's the maximum speed of the tram during this journey? 15 is the biggest Y value I see, so it's 15 meters per second. Calculate the distance traveled between positions M and N. Well, distance equals speed multiplied by time. 100 take away 40 is 60 seconds. You're traveling at a speed of 10 because we can see that on the Y value. So it's 10 times 60, which is 600 meters. Okay. Calculate the acceleration of the tram between M and N. So phi minus U, sorry, A equals phi minus U over T. So N and O is what we're looking for. So your phi value is 15 because you start off at 10. See N to O, I'm just going to highlight it in red here. You start off at 10 meters per second, and then by the end of the journey, end of that period of time, you're at 15. So phi is 15. Your U value is 10. The time taken is 100 to 140, which is 40 seconds. So it should be 15 take away 10 all over 40. Now you're going to find this a fraction answer. So put the fraction in here. 15 take away 10 divided by 40. Answer is 18.125. ms2, or 18 meters per second squared. What are the units of acceleration? Just did it there, meters per second squared. Describe the motion of the train between P and Q. Well, where is P and Q? P and Q. It starts off at 15 and it ends up at 0. This means it decelerates. So it decelerates from 15 meters a second to 0 meters per second. Decelerates means you're getting slower. 15 meters per second to 0 meters per second. Okay, all good. Now, a stone was dropped from top of tall cliff. The stone's approximate velocity was measured as it fell. The data collected during the experiment is given in the following graph. So once again, guys, this is a velocity time graph. Okay, so it's a velocity time graph, so it's not distance, okay? The first thing I want you to do is define velocity. We did it already. Velocity is speed in a given direction. A given direction. Example, 15 meters per second in a direction in a northeastern direction. Sort of like what they do on the news with the wind. Okay. Use the data from the graph to estimate the acceleration of the stone as it fell. give the unit acceleration. All right, so pick 2 points on your graph, any 2 points on your graph. So we'll pick 0, 0, and then we'll go to the very end, which is 5 seconds, 50 meters, 50 meters per second. So our phi value is 50 because it's traveling 50 meters per second at the end. Our u value is 0. The time taken to get there is 5 seconds. So it's a equals phi minus u over t. So it's going to be 50 take away 0 over 5. And then 50 divided by 5 is 10 meters per second squared. If you take any 2 points like this, you'll get the same answer. So imagine I took the 2 blue points. So what's that? 220 and 330. This is a phi value of 30, a u value of 20, and the time in between both points is 1, because difference between 3 and 2 is 1. And then you can do the same formula again, where you do 30 take away 20 divided by t, which is 1, and you still get 10 meters per second squared. So same answer no matter what. Name the force that caused the stone to fall. Force of gravity. Okay. Stone had a mass of 2 kilograms. What was the weight of the stone on Earth? Well, weight is mass multiplied by gravity. So it's 2 multiplied by 10, which is 20 newtons. Okay. Next one, question 7. I believe we're on to volume. The volume of a block is its length by its width by its height. So it's going to be 4 multiplied by 8 multiplied by 2, which is by 8 by 2, 64. Now remember, it's measured in centimeters, so volume is centimeters cubed, area is centimeters squared, and length is centimeters. Or it could be meters, meters squared for area, and meters cubed for volume. Depends on what they give you. Okay. Calculate the density of the block. Well, density equals mass divided by volume. So it's 128 grams divided by 64 centimeters cubed. This will give you 2 grams per centimeters cubed. Okay. Next question. The photograph shows 3 glasses of water labeled A, B, and C. The egg was placed in each glass. The photograph was taken when the eggs were stationary. Which glass, A, B, or C, contains the egg with the greatest density? Well, whichever egg sinks to the bottom has a density greater than water. If it's flowing in the water, it's equal pretty much to the density of water. And if it's floating at the top, it has a density that's less than water. Okay, so we call it which glass? C, because the egg sinks to the bottom. The bottom, which means it has a greater density than water. Okay, good answer. Now, let's move on. Question 8. The mass and volume of a cork are needed to calculate its density. Name a piece of equipment used to find the mass of a cork. We use a mass balance, or some people might say a weighing scales, okay, to find the mass of the cork. The volume of the cork can be found by submerging it in water and measuring the volume of the water displaced. Explain how you would submerge the cork in water. You could put a pin in it, put a metal pin through the cork, to submerge it through the cork, and then push the cork using the metal pin beneath the surface of the water. Essentially, this is water. This here is my pin with the cork in it, and what we're doing is we just push the cork just under the water like so, and then we can find out the volume that way to get it underwater. Okay. Now we have liquid A and liquid B. Give a reason why the water sinks under liquid A. What you say is the water is denser than liquid A. Okay. Give a reason why water floats on liquid B. What you say is the water, liquid B is denser than the water. Okay. So next one, question 10, I believe. A cylindrical block of wood has a radius of 2, a height of 7, and a mass of 66 grams. Calculate the volume of the block. So a volume of a cylinder is pi r squared h. Okay, so what you do is you say pi, radius squared is 2 squared. You multiply by height at 7. Find the pi button in your calculator. See this little yellow button here? So you press shift to activate the yellow buttons. Press pi. Then you press 2 squared, multiply by 7, and 28 pi. Change that to 87 point, call it, see the way it's 964, the 4 rounds down, so 87.96 centimeters cubed. Calculate the density of the wood. Well, density equals mass over volume, which is 66 grams divided by 87.96. So 66 divided by 87.96, and we get roughly 0.75, so roughly 3/4, 0.75 grams per centimeters cubed. Okay, and now we're moving on. Bobbing for apples is a traditional Halloween game. A large basin is filled with water, and apples are put into the water. Players try to catch the floating apples with their teeth. Why did the apples float in water? You can say apples are less dense than water. Or apples have a lower density than water. Okay, describe with a label diagram how to measure the density of an apple. Okay, so first thing we need is to density equals mass over volume. So we need to get the mass. The mass is the easy one. Yeah, so here's the apple. Okay, make sure you label your diagrams. Apple, and let's for argument's sake say 200 grams. Mass balance. So we've measured the apple as 200 grams, okay? Next, to get the volume, we use an overflow can. Which you have to fill to the brim. Okay, then underneath that's just like a box or a piece of wood or something like that. So this is my overflow can. So we need to label everything. So there's a box, This is an overflow can. Water. Nope, I'm going to get in the way of myself there. So overflow can. We got water, which is in the middle. And then we have is your graduated cylinder. So just make that the spout. Spout. Graduated cylinder. Graduated cylinder. And then we need to place a pin into the apple and then submerge the apple underwater. Okay, so we just have apple and pin again. So this is the apple, this is the pin, and then we have the overflow of water coming out and into the graduated cylinder, which measures the amount of water. So for argument's sake, we could say, I don't know, it doesn't really matter what the numbers are, to be honest. Okay, so I'm gonna have to describe this, haven't I? So it's described with the aid, so I'm gonna have to write down a bit of wording on what to do with this. Okay, so just give me a second. We're going to describe it. I'm going to type out this answer as well. So, part 1. Get the mass of the apple by placing it on a mass balance and take a note of the apple's mass. 2. Place a metal pin in the apple. 3. Fill an overflow can to the point it starts to overflow. Water comes out the spout, you mean? 4. Place a graduated cylinder under the spout of the overflow can. Number 5. Use the pin to submerge the apple in the overflow can. You will notice water starts to overflow. Overflow into the graduated cylinder. And finally, number 6. Where are we? 26. The volume of water in the graduated cylinder is the volume of the apple. Part 7. To get the density of the apple, divide its mass by its volume. And you're done. Okay. Why do icebergs float on water? Icebergs float on water because ice is less dense than water. Pupils measure the volume of a potato in the laboratory using labeled A and B as shown. Name the items labeled A and B. A is an overflow can. B is a graduated cylinder. The potato has a mass of 175, so we got to calculate density. Density equals 175 over 125, which is 1.4. Why did the potato sink in water? Because the potato is denser than water. Okay. Now, ice floats on water but sinks in ethanol. Use this information to compare the density of ice with the density of water. Okay, so ice floats on water, so ice is less dense than water. And compared to density of ethanol, ice is denser than ethanol. If it sinks, it's denser, and if it doesn't sink, it's less dense. Describe an experiment to show the expansion of water when it freezes. Okay, so what you can do is you can get a glass bottle. You're not to do this at home, by the way, because the bottle will break and there will be broken glass. You fill it full of water. That is the world's worst bottle. Oh, there we go, a bit better. So it says glass bottle filled with water. Water. Okay, and then you put it into a freezer. Okay, so here's what happens. Fill a glass bottle full of water. Fill a glass bottle full of water and place it in a freezer. Next part. Leave in the freezer for a few hours. When you come back, when you open the freezer, you will notice the glass has broken. This is because when the water changed to ice, it expanded and broke the glass bottle. Okay, that's it.